Okay, so first, thanks to the conveners for giving me the opportunity to give this talk. I was asked to talk about generalized TMDs, in particular focus on definitions of TMDs and in particular meaningful definitions. And what I'm going to talk about is based basically on this paper. Okay, so what are GTMDs? What does this acronym stand for? Well, it's generalized transverse momentum dependent pattern distributions. And naively, they're defined in terms of such a matrix element where we take the usual TMD operator, which is a bilocal operator, and consists, if we talk about quark GMDs, quark GTMDs, and that's all I'm going to cover in this talk. So then we have two quark fields that are separated not only along the light cone, but also there is a transverse separation. And if we take the Fourier transform, then this operator depends on the longitudinal momentum fraction x, the typical one, and the transverse quark momentum kt. And then we sandwich this operator, and in usual ordinary TMDs, we would just take a diagonal matrix element. For GTMDs, we take an off-diagonal matrix element. So the momenta of the incoming nucleon and the outgoing nucleon P and P prime are not the same anymore. That means we can basically take the same off-diagonal kinematics that we know from GPDs. We can work, for example, in this symmetric frame, work with the center of mass, momenta capital P and capital delta. This is kind of like the average nuclear momentum P plus P prime over 2. This is the momentum transfer transferred from this nucleon to this nucleon. Well, the psi is the longitudinal momentum transfer, and T is kind of like related to the transverse momentum, the transverse component of this for momentum delta T. We can parameterize this matrix element. It's basically a correlator, so we can parameterize it in terms of coefficient functions, and these coefficient functions are then the GTMDs. For example, if we take unpolarized quarks, that is the case if this gamma matrix is just a gamma plus, then we can parameterize this thing. Well, we did this for quarks for spin 0, hadron in this paper, for spin 1/2 paper target in this paper, and later on Barbara and Cedric, they repeated this exercise also for gluons. And one ends up with such a parameterization where we just numbered these functions f1, 1, f1, 2, f1, 3, and f1, 4. I will also, if we do the same thing for longitudinally polarized quarks, which would correspond to gamma plus, gamma 5, then we could call these, or we call these G functions, GTMDs. And these GTMDs are functions basically on 5 kinematical variables. The longitudinal momentum fraction x, the variable psi, and also on the modulus of these two vectors, kt and delta t, and basically also on the angle between kt and delta t in the transverse plane. Now, very important in this definition is what is called the Wilson line. That's important in particular for transverse momentum dependent objects. The Wilson line is a path-ordered exponential of Luan fields, and in the exponential we have a contour integration which is determined by a path, and this is what is called the Wilson line. And this Wilson line makes this bilinear operator color gauge invariant. A priori, it doesn't matter which line you take in order to connect the two arguments of the two quark fields. You can basically take any line you want, for example, a straight line. But in the TMD business, it's kind of like it's it's common and natural to work with so-called staple-like Wilson lines, which is like you start at one specific point, then you move along the light cone up to infinity, go in a little bit in a transverse direction, and then come back to the other point. And you can go basically in the plus infinity direction, which is called future pointing Wilson line, or in minus infinity, which is past pointing Wilson line. And in the TMD business, the future pointing Wilson line is what we expect for semi-inclusive DIS, and past pointing Wilson line is what we expect for the Brilliant process, for example. So also we're also going to adapt these staple-like Wilson lines for GTMDs in order to get a connection to the ordinary TMDs. And if we take these staple-like Wilson lines, there is no constraint from time reversal anymore, which means that these GTMDs become complex functions. So they have a real part and an imaginary part. And the imaginary parts of these GTMDs, they show the same sign flip as we know for example, in odd TMDs. And so the imaginary part of a GTMD in semi-inclusive with a future pointing Wilson line would be the same as the imaginary part of the GTMD with the past pointing Wilson line up to a sign. Yes?
Very stupid question. So time reversal is anti-unitary.
Yes.
This is the minus sign received, right?
Yes. I mean, it's the same. You can do the same proof as you do for the inverse function. That's the result of it. It's actually, yeah, you actually apply PT transformation. Okay, so why are GTMDs interesting? In particular, with staple Wilson lines, they may be viewed as unifying functions or mother functions of GPDs and TMDs. So if GPDs and TMDs describe two sides of a medal, then the GTMDs are actually the medal. So what it means is that the GTMDs you can recover TMDs and GPDs by going at least naively to different limits. So if we take the GTMD and make it a diagonal matrix element, that means delta goes to 0, then we recover the TMDs. If we take our naive matrix element and integrate on the level of the matrix element over KT, then we would recover the GPDs. And we then go, if we then reverse the limits, then we end up with ordinary pattern distributions. Now, it's also interesting that GTMDs are related to Wigner functions, and Wigner functions have been introduced by G, and Yuan, and then elaborated on by Cedric and Barbara. So, the Wigner functions in ordinary quantum mechanics is defined like this. So you take the wave function of a system at a certain variable x, and then you make a little shift plus y over 2. Then you multiply it by size complex conjugate psi, and make this shift, but in the negative y direction. And then you make a Fourier transform with respect to y, and this gives you kind of like a function which depends on the location and the momentum, and it's not really a phase-space distribution because this is not positive definite, but it's very useful to calculate, for example, expectation values. So it's a nice concept in quantum mechanics. This concept has been translated by G and Yuan, G. Belitsky in these two papers to QCD, where you basically take this expression and you take this expression here and you replace the wave functions kind of like by the operators. Yeah? So you have Q bar Q here. And then you sandwich this operator by an off-diagonal, through an off-diagonal matrix element, and then kind of like translate this into impact parameter space at psi equal to 0, which was discussed by Matthias earlier. And this is how the Wigner function is defined in QCD. And Barbara and Cedric, they found out that these Wigner functions are related to GTMDs upon a Fourier transform. So we take the GTMDs and make a Fourier transform with respect to delta t, and this translates it to impact parameter space, and we take psi equal to 0. Yeah. And again, these Wigner functions are really nice in order to get really an intuitive formulation of quark orbital angular momentum and also on spin orbit correlation. For example, you take the Wigner functions for unpolarized quarks, and then you just take the classical orbital angular momentum, kind of like the orbital angular momentum in the z direction, for the impact parameter space and the transverse quark momentum, and then you integrate over everything. It's kind of like gives you an expectation value of the orbital angular momentum. And then Barbara and Cedric showed that this is directly related to the kind of like the first TMD moment of this GTMD F1,4. So that's F1,4. It's related to quark orbital angular momentum. Of course, at psi equal to 0. And also here you would take the limit of delta t going to 0.
So what's the expected large K behavior of this F1,4?
I'll come to that.
Okay.
In 2 slides. Yeah, and the same can be done for the spin orbit correlations. If you have a longitudinally polarized quarks in a nucleon, it's basically the same thing, but for the GTMD G1,4. Okay, so for a long time, there was the statement GTMD cannot be measured in, or we don't know any hard exclusive process where GTMD appear. And also here there has been some progress by Andreas and collaborators. Recently they suggested a kinematic process where these GTMDs appear, and that is exclusive double Drell-Yan in pion nucleon collision. So we have a nucleon coming in here, a pion come in here, and the pion annihilates into 2 virtual photons, and the proton stays intact. And this is kind of like a picture which reminds me of double parton scattering. And in this paper they claim that also the gauge link is a staple-like gauge link and pass point. So I guess, with respect to that, we're on the right track. And they gave formulas for the amplitude of this process, at least at tree level. And here we see that we have the typical TMD convolution integral of a GTMD with the pion light cone wave function.
So is there a handbag-like contribution to this process?
That would be a single parton scattering if
the 2 virtual photons
from the same line. I guess so, yes.
Is it suppressed?
It should be suppressed. So for GTMDs, one has a similar argument. That's a pion nucleon going to a single dielectron pair at nucleon. What people have discussed, and there's a similar argument if you have like this single quark line connecting the 2 soft blobs. You get the suppression formally. I mean, in practice, one would have to see. I mean, how large virtualities one has to go.
I'm confused. This looks like really a double parton scattering to this kind of Drell-Yan-like thing, but why it's not described in terms of the double parton distributions? Naively, the diagram.
Because the nucleon stays intact, right?
It's off forward.
Because.
And you get, in this leading order, you get actually only contribution in the urban region.
I see.
And so what's
the
hierarchy of scales? You'd say that the mass is the gamma star here versus the center of mass.
Well, there's many scales, right? There's the
basically you just you say large center of mass energy and post virtualities of the photons large.
I mean, there's presumably a hierarchy between these scales.
Well, I guess the photons need to be back to back, right? So that the transverse momentum, the delta t, has to be small.
Invariant mass, yes.
Is the invariant mass of the
Of
gamma star
two
gamma,
gammas,
is
yes,
it of,
yes,
is it of order S, or is
This is, you mean the invariant mass of the two gammas?
two gammas, yes.
That's actually not so relevant. I mean, what we require is that both virtual photons have a large invariant mass. Maybe one could actually relax a little bit on that condition. In fact, I mean, I don't know if you're going to mention that. I think
No, that's all I'm going to say about that.
Since Mark talks about potential observables for these, there's been a lot of progress, especially in the small X region, in the last years. Tucker was involved.
Yeah, I think Feng will also talk about it later on.
So to address GTMDs of gluons in particular, I think this is pretty exciting and could really be relevant for PLC. Okay.
Yeah, and another, as you said, and in this particular process we probe the quark GTMDs in the urban region.
I think this is a statement probably strictly valid only at least.
Oh, okay. All right. So yeah, and I mean, you also recently wrote a paper for gluon, basically the same process, but for heavy quark production. Then you have gluons in here, and Feng will also talk about Wigner distributions in the small X frame. Okay. All right, so let's go back to the definition of GTMDs, and for some reason, a few years ago we had a look at the large KT behavior of GTMDs, and at large KT you can directly calculate perturbatively the perturbative tail, and you assume that this large transverse momentum of this quark is generated by perturbative gluon radiation. So you could calculate these diagrams in a regime where KT is much larger than lambda GCD, and we basically repeated a calculation that was done in this paper for ordinary TMDs, and kind of like repeated it for GTMDs. Here, we took the naive GTMD definition, the one that I showed in the beginning, and used this gauge. It's basically light cone gauge, but you tilt this light cone vector a little bit off the light cone. So you get an additional parameter zeta here, which controls how far away you go off the light cone. And this calculation seems to work. For example, for f1,4, you calculate these two diagrams, you get a well-defined expression, and you match it, this f1,4, to the GPD H tilde of Q and G for quarks and gluons in these two diagrams. And you see that kind of like the KT and the delta T here mix. Yeah, they appear in common denominators. If you set delta T equal to 0, then you see that this function drops like 1 over KT to the 4.
Excuse me, why there is no gluon emission from the gauge link in this case? I mean,
well, we set
this normalized at some scale.
We set this particularly to 0. We chose this gauge.
Okay.
Yeah. I know it's a little bit dangerous, but
it's not intuitive. I mean, it's basically an inclusive object, so you should be able to emit one on one side and then have it
well, the gauge link in a way reappears in this propagator through the numerator of the propagator. Well, the point is,
b dot a equals 0. That refers to one.
It's kind of like
a direction.
If you take n times a, it would be would be light cone gauge, right? And then you get these. It's a bit dangerous, so you have these singularities, these spurious singularities that we actually come to my next point, that we actually do meet for other GTMDs. For example, for f1,1, you get this logarithm of zeta, which kind of like this light cone divergence, represents this light cone divergence. So we see that the naive definition is kind of dangerous. And that's actually
with that choice of gauge, we use the standard TMD renormalization.
Yeah, we check that if we let a delta to go to 0, then everything reduces to the results in this paper. Where they also studied the perturbative tail of TMDs, not GTMDs.
I have a question. Those are two off diagonals? Or,
yeah, they are off diagonal.
So question, why there is no recorrection to Coulomb correction to these 4 lines? So
that would be irrelevant for the perturbative tail. That would be proportional to delta k, would be proportional to a delta of kt. Yeah. Okay, so the whole point of this was to show that there is a problem with the naive GTMD definition, and that is expected. I mean, you know that from TMDs that you have to do something more. Yeah, so in this paper, we defined a modified definition of GTMDs, and since these problems arise from the operator, we followed the same. We did the same modification of the definition of GTMDs as we did for as it's well known for TMDs. Yeah, it's the same operator, so you can do the same thing. And in order to have a meaningful definition for GTMDs, there are 2 criteria. I would say, one, you should have a meaningful way to renormalize this matrix element, so that should be possible. And one should also have this matching to at large KT or small transverse separation to collinear GPs. So these Wilson definitions that we can calculate, there shouldn't be any logarithmic divergence. Yeah.
So I mean, your soft factor is a vacuum expectation value. So how do you take care of the fact that you have a momentum transfer by your operator? Doesn't that change the divergences as well?
No, it doesn't. So the ultraviolet divergences they come from the operator, not from the.
But you have more operators. You have total derivatives, for example, that not just internal derivatives in the standard OPT. And I mean, if you have a non-forward matrix element, a lot more operators can have non-zero matrix element. You just like total derivative operators. You just never see them in the forward limit because they.
Well, I think that should appear in the Wilson coefficients. But so what we so we did the usual inclusion of the soft function that we know very well from TMDs. That is, we include this vacuum expectation value, and then we do one loop calculation. So since renormalization comes from the operator, we calculated the GTMDs in a modulus support target. Yeah, and that boils down to basically these 3 diagrams. And in order to regularize in order to regularize the light cone divergences, we used what is called the delta regulator. The delta regulator is basically you have a propagator, and then you have the I epsilon or I delta description. And the idea of the delta regulator is then, if you work in dimensional regularization, you first expand in epsilon, and then in the dimensional you first perform the dimensional regularization, and then let delta go to 0. So it's basically an exchange of limits. And we have the delta here and the delta here, and it's a regulator. In the end, it should go to 0. But here, the mass dimensions, they don't match with this here, so we have we introduce an additional scale lambda squared. Yeah, and if you do this, the calculation of these diagrams, then that would correspond to the naive GTMD definition without the soft factor. We find this expression. You see again, all these are just the virtual diagrams. They are proportional delta 1 minus x delta kt. But we see that we get 3 over 2 epsilon, which is fine. It's an UV regulator. But then we have this overlapping UV and soft divergence. So we have 1 over epsilon times a log delta. And that, of course, if you have that, then it's difficult to have a meaningful subtraction constant, just to subtract away these poles, right? And here we see that the soft factor helps. So we calculate this matrix element to order alpha s and just take the ordinary, just the leading order naive matrix element, and then we see that this contribution from the soft factor exactly cancels this overlapping divergence. So here we get the plus 2 over epsilon times log delta, here minus 2 over epsilon times log delta. We add everything up, and we see that this overlapping divergence canceled. And then we can just read off the renormalization.
What is actually mu?
Mu is the renormalization scale that you introduce through a dimensional regularization. This lambda comes in from this delta regularization.
When you identify lambda.
Yeah, I mean, in TMD evolution, you always have 2 scales. Okay, so but in the end, basically everything is the same as for GTMDs is the same as for TMDs as far as evolution is concerned. So you have the renormalization constant. You can from that you can derive the enormous dimensions, and it's the same. Yeah. So here we have kind of like the input-output version of TMD evolution. So the GTMD at an initial scale, mu0 and lambda 0, and you basically, and this is all in VT space, in coordinate space, by the way. Yeah, so, and you just have the perturbative Sudakov factor, non-perturbative Sudakov factor, and we take the same input that was known for the quark TMD. Yeah, and then we in order to illustrate how this works, we just did the same thing as people do in the TMD business. We come up with a Gaussian model for the KT squared, which actually works very well at low scales. The x dependence here is then given by a GPD instead of the usual pattern distribution, and this is an illustration how the KT distribution flattens out if we switch on evolution. Yeah? And it flattens out just like TMDs. Now, the other criterion we had for a meaningful definition are these Wilson coefficients. So we can kind of like, if the transverse distance of these two quark fields are small, we can kind of like make an operator product expansion in the small coordinate space, and typically it's called VT, small VT or ZT, and one should not confuse it actually with the impact parameter space. Yeah, and this is this is the statement basically of this operator product expansion, and what we want to do is we want to calculate these Wilson coefficients perturbatively. And in particular, if this definition is a good definition, then these Wilson coefficients should not depend on this regulator delta. Yeah, and to show this, we also did the calculation for a massless quark target. So the 0th order of these Wilson coefficients is just the delta function 1 minus z, and we can calculate the first order, the order alpha s, just by calculating the GTMD to order alpha s, the GPD to order alpha s, and then subtract. Yeah, and in order to calculate this, we need the real diagrams in the quark target model. This corresponds to these 3 diagrams, and one can readily calculate them. And this is what appears, for example, for the GTMD f1, 1, and you see that this is already quite a complicated expression. And this piece is actually the contribution from the soft factor. So the soft factor also introduces real diagrams. This is what appears here. And in order to calculate the Wilson coefficients, we have to transform this to BT space. Yeah. And you see that this is not an easy task analytically to do for this with the non-zero delta t. So we already set psi equal to 0 in order to simplify expressions, but delta t really complicates this Fourier transform. What we can do is if BT is 0, if BT is 0, then this means we just perform a KT integration over this expression, and this can be done analytically. Yeah? But if we really have a BT, non-zero BT, the only way to do this is to apply numerics. And so what we can show, we boil it down to a 1-parameter integral, these Wilson coefficients after Fourier transform. And what we find is that we have a contribution which is independent of this cutoff delta or of this regulator delta, and it's given in terms of plus distributions, some plus distributions. And then we have a second term, which is chi, which boils down to this, an expression which is proportional to log delta, another log delta, and then this is a 1-parameter integral, which I cannot do any further analytic. And it's given in terms of some derivative of certain modified Bessel functions where delta explicitly appears through this square root. Yeah. Okay. What we can show is that if we set psi equal to 0, so actually this is already done here, what one can show analytically is that these expressions are actually real. And this is an important test because we expect these Wilson coefficients to be real because there's this kind of like impact parameter interpretation for GTMDs that we want to recover. So that's important. What we also recover is if we take this complicated expression and set delta t equal to 0, then we can actually perform this 1-parameter integral and we recover the usual TMD result. Also very important. What we can show numerically is, not analytically, but numerically, is that the limit delta to 0 seems to exist. Yeah. So this is not apparent from this formula, but we can take this limit. For example, here I've plotted the Wilson coefficient with a certain test function, take the integral over x from 0 to 1, and then just plot it. And I plot it versus some values of delta. And delta explicitly appears here and here, and so on. and then I shrink it numerically, and I go down to the smallest machine precision that is available, and it really seems that that there is a plateau here, that it doesn't actually depend on that. And yeah, this is as far as this is concerned. So it seems that this is a meaningful definition. We want to go on with this work after we took some 2 years break or so, but we want to actually work on this furthermore. What we want to do is to implement these Wilson coefficients, also go away from this input-output prescription and implement the Wilson coefficients in the GTMD evolution, and then probably need some matching procedure between the perturbative and non-perturbative input. This is also well known, for example, through the E-star prescription. What we're really after is the herbal region, because that's the region that can be probed in this process that have just been proposed. And it's probably a good idea to try other regulators, because the herbal region and the DGLAB region, they're kind of separated through contour integration, and that kind of interferes with this I delta prescription. So we want to try if other regulators work better, and here in particular in soft collinear effective theory, people use different regulators, more better regulators, and we try to implement this at all as well. This is where I'm finished, and thanks for your attention.
Just to make sure you did this calculation at finite C?
No, yeah, at C equal to 0.
All the results short days, yes.
Yes.
So this soft function looks exactly like a soft function.
Yeah, it's the same.
So my question is, this will turn out to be useful if you find a process where the effect like is 0 in terms of GTMD and soft function. Then you will be nominally.
Yeah, of course. Also, the definition of some Wilson lines must come from a process. Yeah. Otherwise, it's just academical.
So I have a question, technical question with this lambda and mu, so we need the scales.
Mm-hmm.
So in this delta regulator, you had initially this lambda, and then you see it's used to set it equal to mu.
Well, in the end, yes, you set everything equal to one scale. I mean, in principle, you could study the evolution in both scales, but what people typically do is to set it to one scale and then evolve it.
But at some point, you wanted some diagrams, some divergences to cancel out. This was possible only for lambda equal mu. No.
How this was possible for any?
Yeah.
Can you remind us what these regulators mean physically? And you have a rapidity cutoff in this table, like Wilson line, or
well,
not everyone here is familiar with the TMD definition with
the
soft factor.
Yeah, the Collins type regulator is really to go a little bit away off the light cone, but then it's complicated. You have these cancellations, but only on the level of the integrand, and before you take any integrations, it's complicated. I think this delta regulator is a straightforward way. You work with the Wilson line along the light cone, but you have these propagators. I mean, it's a regularization that I think only works perturbatively.
Yeah. Is there a physical meaning to it, like you limit the rapidity of emissions that can come from the Wilson line or something like that?
I haven't thought of a physical meaning. I think it's just a mathematical trick.
So maybe you can add a comment to it.
this is connect in some sense. This is all related to rapidity. Then, in a sense, related to infrared part. If you have a real good factorization, then hard part and the matrix and mass part, they should separately have preserve, taking care of all the infrared elements. Only thing between them is the collinear. So in the collinear normal factorization, you can also solve the line, Wilson line, because there are no transverse separation, you can take care. But once you allow transverse momentum, those soft Wilson line will have separation. So they have divergence at the end. Then what happens is then you can have, and you how you factorize it. So you want to factorize in such a way in TMD, take care of all the infrared divergence, all the thing left the collinear behaviors. Then the corresponding hard part take care. Well, the GTMD, as Mark said correctly, these things relate to the operators because they don't care whether it's a proton or high or long distance physics. So that they will have same behavior as a TMD. But the regular itself, you don't have to choose the regular. As long as you preserve certain symmetry, you don't break the symmetry. I think this delta prescription is just say analytic continue to work imaginary plane rather than have a linear along the Lycon line, P by angle to 0. I let the system go to imaginary instead of column so-called initial plane. I turn the frame with it. If I'm interested in something related to the choice, I'm in trouble. So, but you're always allowed to go to imaginary plane. So that's an advantage in some sense.
Just a comment also on what Long was saying. I mean, ultimately, of course, we hope that we make further progress. How we well in identifying processes and having all-order factorization theorems with all the bits and bytes and soft factors, but having a definition which you can take literally, and this is what Mark was talking about, is also crucial for lattice calculation.
That's true. We want to take care of all the infrared and stuff.
Yeah. And I mean, this is really this nice application already on the market where you can study some of the transition from the Jeffrey Manor, as you said, to the G orbital angular momentum using these tools.
Okay, I have a question somehow for you. So you expect that this definition is already in valid in all of them, yes?
So we are not talking about process. So just about
I
the
am talking
operator.
about the factorization.
This is what one would hope.
Yeah,
I mean,
first, we need the process, right?
Even for the TMDs, in a sense, there's no all-order proof. And probably to be careful what I'm saying now. Probably no all-order proof that the definition which takes care of the rapidity divergences does the job.
For PDF, there is an original paper by Colin Sokol. PDF definition solved in infrared save, except the collinear. And for TMD, John tried that proof in his book. So if you put a soft factor, you are self-consistent to remove infrared on the left collinear. Because collinear divergence is an artifact of determined calculation. If you calculate on a lattice, there's no real collinear divergence. But you have to make sure the operator itself will be infrared.
So I think the statement which one can probably safely make is as long as psi is 0, the definition which Mark was presenting is as good as what we have for TMDs.
Is there any other form of any other experimental link to it apart from Trillium? Is there anything to do with electron scattering?
We would have to think. I'm not aware. Maybe you have.
No, I mean at least in the small X region.
Okay.
You mentioned it earlier. There's a lot of progress, let's say, and I think this is where the electron ion could play a role.
Yeah, we did some work, but not for the quark GTMD.
Yeah,
we did only for the gluon GTMDs. I mean, the small X region, I think it's measurable.
I think for the quark GTMDs, that's your process is
So
the only
far, it's
process
the
that's on the
one which
market.
is forward. Of course, it
Especially in lava,
would be nice to see more and really have a relation also for the quark GTMDs in EP scattering.
Maybe we could add a comment to what you said. It's a slight different from this double scattering like related, because this is, you have to be exclusive.
Yeah.
To be an invention. Double scattering people have it's not that.
Which means that in most of these processes, proving factorization would be quite difficult.
Any further questions to Mark or comments on